right. So I'm going to go ahead and get us started so that we can move through this and get through everything on time. So just a quick reminder to keep yourself muted and to turn off your camera while we have this talk. All right, so hello and welcome everyone to the International Year of Sound, Acoustical Society of America's virtual speaker series. I'd like to thank you all so much for tuning in, and I think we're gonna have a really good time today. So let me first introduce myself. My name is Keita Jones and I am the ASA Education and Outreach Coordinator. My job is basically to support ASA members in all of their efforts to increase awareness of acoustics with educational and informal outreach programs like this one, actually. So I also want to briefly tell you a little bit more about the ASA. So as you can read here, the purpose of ASA is to generate, disseminate, and promote the knowledge and practical applications of acoustics. And thankfully, we can do that with our great membership. So we have over 7,500 members who work in acoustics throughout the US and really around the world. And there are a variety of fields related to sound that are represented by our members and the structure of ASA. So for example, here are the technical areas. We have 13 technical committees and 1 specialty group. We've got the acoustical oceanography, animal bioacoustics, architectural acoustics, biomedical acoustics, computational acoustics. That's the technical specialty group. That's our newest one. There's engineering acoustics, musical acoustics, noise, physical acoustics, psychological and physiological acoustics, signal processing in acoustics, speech communication, structural acoustics and vibration, and finally, but not least, underwater acoustics. It is quite a bit of representation here. If you'd like to learn more about all of the scopes of these various committees and how they operate within ASA, I encourage you to visit acousticalsociety.org, and there you can see all of the websites and visit all of the technical committees if you'd like. If you are more interested and want to explore acoustics more broadly or more generally, or if you're actually looking for some educational materials, I recommend you visit exploresound.org. So the Committee on Education developed exploresound.org for young people and for educators who are interested in learning about sound and the scientists who study sound. The site has resources for both students and educators. There are games, science fair projects, acoustician profiles, class activities, and really a lot more. So if you want to find a lot of information, definitely go to exploresound.org. And then you might just in general be interested in the International Year of Sound. So you should visit sound2020.org. There are all of the international events and everything that's ongoing for 2020 and going into 2021. And I definitely recommend that you check out specifically the student competition. This is a song competition for K through 12 students. They can write lyrics and they can make art, and there are cash prizes. So definitely check that out. I'd also like to ask you all to go ahead and mark your calendars for the 3rd speaker in this series, Nicole Holliday, and her talk, which is entitled, "It's in the Tone, the Acoustics of Social Judgments and Linguistic Profiling." It's going to be a really good time. The registration information is available on exploresound.org. So we hope to see you there in 2 weeks. Okay, so just before I introduce Dr. Andrew Morrison, I do want to give you all a few reminders. So go ahead and keep your microphone muted and your camera off. There will be a Q&A session at the end of the presentation, so you can go ahead and post your questions or comments in the chat. This talk is being recorded and it will be posted to the ASA YouTube channel at youtube.com/Acoustical Society of America. go ahead and click subscribe so that you'll be notified when this talk goes up. So for example, I've got on the screen here, this is our channel. So 2 weeks ago, we had our talk with Anne-Marie, playing with sound, and her talk has already been posted. So you can go and check it out anytime. Okay, so I think I've probably talked for long enough, and you all have actually tuned in to hear what Dr. Morrison has to say. So I'm gonna go ahead and turn off my camera and stop sharing my screen so that Dr. Morrison can go ahead and get his all situated.
Thanks, Keita. Whoops. Okay. All right. Thank you. Thank you for tuning in. Thank you, Keita, for that introduction. I'm going to be talking today about, I'm calling this talk Making Meaning from Data, and it's all about how we've looked at the physics and acoustics of the Caribbean steel pan. So here's today's story sort of broadly described. I had a question about something that had not yet been explained by science. And I think maybe it still hasn't been explained by science. And the basic question is, what makes a steel pan sound the way it does? So that characteristic, distinctive sound that a steel pan has, what gives it that? That's the big question. And to answer that question, I did some experiments with my collaborators, and then analyzing that data took some surprising twists. But I think that this story overall says something not just about acoustics, but the nature of science. So we'll get into that just a little bit. But really, what I want to focus on is the analysis of the data and how we got to where we are today. So I can't not talk about the steel pan, just the history of this fascinating instrument. I claim, and others have claimed, that it's the most significant acoustic instrument invented in the past century. If you can think of another tuned acoustic instrument that you don't plug in, it's not electronic, or not electronically amplified, that is as significant as the steel pan, I want to hear about it, because there are lots of new percussion instruments, but they're not. Most of the new ones are not tuned and have not been as widely adopted as the steel pan has. It's only been around for about 75 years, and I keep having to update this number. Oh, I forgot. I'm gonna turn on my captions and my pointer. It's only been around for about 75 years. I keep having to update this. The 75 years sticks out to me as something I may need to update, because the steel pan comes from the islands of Trinidad and Tobago. It's a country in the South Caribbean. And, about 75 years ago, we were towards the end of World War II. And right leading up to World War II, these islands had, they were a colony of Great Britain, and had helped in the war effort because they were a source of oil for the British. And also the waters around there served for naval testing, both for the United States and for Great Britain. And as a result, this instrument grew out of the surplus of oil barrels that the country had access to. And I don't claim to be a representative of Trinidad and Tobago, and but I do think that this is one of the great gifts that that this country has given to the world, is this musical instrument, which is really distinctive in its sound. And you can go all over the world, and there are people that play the steel pan. So it's a really testament to the acceptance of this instrument all over the world. So if you look at it, it looks really, really simple. It's a curved piece of steel with some notes that have been tuned into it, but the acoustics of it and the physics of it are actually deceptively complex. So just some terms so we can kind of understand where I'm coming from. I keep calling it a steel pan, and many people, at least in this country, will know it as a steel drum. A the steel pan refers to a single instrument that a single performer plays, but a single performer may play on more than one barrel, or more than one it's what we refer to as the drum. So for example, this set of 6 drums here is one steel pan. That's one instrument played by one panist. But the lead pan maybe is a single pan that is also played by a single performer. And then there are the other parts of it which may have 2 pans, and then like the double second, and there's all different parts of the steel pan family. So together they make a steel pan orchestra, and can be incredibly exciting to listen to when they're all playing together. I want to say a little bit about the tuning process, just to give you an idea of how this works. All steel pans are tuned by hand. There's one step in the process which some tuners choose to automate a little bit, but to this day, there's no factory that is churning out steel pans on a mass manufactured basis. It's a multi-step process. I'm going to go through a few of the steps. And as with most instruments, this process developed through trial and error. So there's no one correct way to tune a steel pan, but there are lots of traditions. And this is even true for the layout of the pan. No tuner is forced to use the exact same layout as everyone else, but there are many traditions that are widely accepted. So the first step in the tuning process is to sink the steel into this concave shape. And these are different shapes for the different types of steel pans. So the base steel pan, the lowest pitched steel pans, are actually going to be sunk the least. So this is the base one. And the ones that carry the lead are sunk the most. And this is the only step that some tuners will use a little bit of automation. Some of them will use pneumatic sledgehammers instead of hand sledgehammers to try to sink the drum down to save a little bit of time and effort. The second step is what is referred to as scribing. The tuner uses a nail set to define the note area. And when I started learning about steel pans, I thought that this was going to be actually a hugely important part of the tuning process in terms of the acoustics of the instrument. But it actually turns out that the little grooves that are put in, which are visually very important for us to recognize where the notes are not actually acoustically very important at all. Then the tuner will shape the drum, which shape the surface of the pan to put a raised convex surface on that concave bowl. And this is the part of the tuning where some of the notes are starting to be roughly tuned in. The whole process of tuning, you should think of this as an iterative process. As a tuner tunes one note, a different note is going to change its the frequencies of the vibrations that note has. So getting one note perfectly tuned without paying attention to the other notes doesn't work. You have to go around and force them into the frequencies that the tuner wants them to be vibrating at. So the very last step in the tuning process is the fine tuning process. And so there's either a heat treatment that is done before this, or sometimes it's done, the heating is done with this. That's a really interesting part of this that I don't have time to talk about. But the tuner uses glancing blows to try to stretch the metal. And this is really where the tuner is not only trying to get the lowest resonance of the note area fixed to the right frequency, but it's also trying to tune the overtones to be in harmonic alignment as much as possible. And then the pan, once the tuning is done, the pan is chromed, and then it has to be retuned because of the chroming process. So here's the layout for the steel pan that we studied. This is a lead pan. It's referred to as a low tenor steel pan. And it uses something called a force and fist layout, which I'll briefly describe a little bit. So notice that every note on the outer ring here is neighbored by the inner ring by a note that is 1 octave higher. So the fundamental frequency for these two notes come in a 2-to-1 relationship. That the lowest frequency on this one is 2 times the frequency of this one, all right? But neighboring on either side of these notes is a note that's either a musical fourth or a musical fifth with relation to this note. And so there are frequency ratios that are important for these. And I'll just talk about the fifth has a frequency ratio of 3-to-2 between the G and the C. All right. So we're going to see that why that's important here in a second. I'll mention that also this particular pan did come to us from Trinidad and Tobago via a tuner by the name of Bertrand Kelman. So the way that I like to study the vibrations of the steel pan and many musical instruments is an optical method, which is a laser interferometry. This is the term is electronic speckle pattern interferometry. We start with a laser. We split the laser into 2 beams here at this element. This is BS's beam splitter, not something else. But the one beam goes through and then bounces off some mirrors and is spread out by a lens and hits our object, which in this case is a steel pan. And then the light is reflected back into through another beam splitter and then into the camera. The other beam bounces off some mirrors and is then directed onto a piece of ground glass and then reflects off the beam splitter into the camera. And it's the interference of those 2 beams at the end that allows us to understand how this object moves. By the way, that whole system is something that anyone could build in their lab with the common lab equipment. It's really straightforward to do. So what do we know about steel pan acoustics, or what was known when we started this? Well, we very well understood how the individual notes resonate. And again, the tuner has put significant effort into making the notes have the lowest resonances be harmonically tuned. So this is the pattern that we see for the lowest resonance. And I want you to, for those of you that have never seen something like this, you should read the concentric circles or the concentric ellipses in this case as almost like a contour map of the amplitude of the vibration of this note. So as we go from the outermost part, which is very bright white color, that is a region where the surface is not moving at all. There's no vibration. And then as we cross each of these circles going from dark to sort of a light gray to dark to light gray, we refer to each of those as fringes. So if I talk about it as a fringe, that's what I mean. But each one of those crossings represents a fraction of the wavelength of the laser light in terms of the amplitude at which the surface is actually moving. So these are examples of a case where we have caused the steel pan to actually vibrate at a very particular frequency, and then we're taking a measurement of the average movement of the instrument. And so this doesn't tell us directly what happens when we strike the drum, all right, but it does give us a picture of what the patterns look like that are embedded in each of the notes. So this is the lowest resonance. This is the second harmonic. So this frequency is 2 times the frequency of this first one. And there's this nodal line where there's no vibration happening right here, which is running in this direction. And then this third one over here is the third harmonic, and the nodal line is essentially perpendicular to this other nodal line for the third harmonic. And so for all the notes in the instrument, the tuner has tried very, very hard to get these to be harmonically tuned, and the patterns look more or less like this for all of the notes. But again, the question is, what causes this steel pan to have that unique characteristic sound that you recognize as the distinctive sound that it has? And the key here is that all the notes in the steel pan are embedded in the same piece of steel, right? It's a lot different than, say, for example, a xylophone, where if you hit one note, the wood for that one note is not directly coupled to the wood for the other notes, right? There's separation between them. But here, this note is coupled to this one. And remember, I said that there is a 2-to-1 relationship between the fundamental frequencies of these two notes. And so when I cause this one to vibrate at twice its fundamental frequency, that has the same frequency as the fundamental frequency for this note. And likewise, there's a 3-to-2 relationship between these neighboring notes. And so when I cause this note to vibrate at 3 times its fundamental frequency, then this one is going to vibrate at 2 times its fundamental frequency, and this one vibrates at its fundamental frequency. And so anytime the panist strikes a note, all of these neighboring notes are caused to vibrate sympathetically. So our question was, can we do something to measure how that behavior happens in the case of a panist striking the drum? And the first idea that we came up with is, well, if we could take our the electronic speckle pattern interferometry technique and use a high-speed camera, maybe we could see something at high speed. And so if you have a collaborator who has a high-speed camera, as I do, then this is something that you can do. And so here's a video of a strike, and I'll let it play again. But this is the note that was hit up here. We actually hit it on the back side so that we could see this happen. So there it goes again. And you can tell very quickly that the wave moves out across the drum. And we're only looking at a very small part of the drum here. Now there is a little bit that's starting to move here at the end, but we'll get to that more. I want to orient you to where we're actually looking at. This is the section of the drum that we're looking at here. So it's only roughly 4-ish notes that we're looking at. And then this is just a single frame that I extracted, I think from later later after the strike. And then here's another example. This is, I'm playing this back at a different speed, not to confuse you, just to let you know. But here we were looking to see if there was any reflection off of the edge of the note, and it was hard to tell. We're not really sure, but this is the only case where we thought maybe there was a little bit of reflection. But you can also see that this note is starting to vibrate, and this note is starting to vibrate, and so on and so forth. So the real question, though, is now that we have this data, these videos, how are we going to actually analyze those videos, right? So my first idea is, okay, I'm going to look at the individual frames. And so here's the frame right before the strike. There's the first frame right after the strike. And then the wave just grows and grows. And then you can tell at this point, the outgoing wave from where the strike happened has reflected off of the surface off of the rim of the drum, and then that reflected wave is interfering with the outgoing wave, and there's now all of a sudden in a matter of 5 frames, it's just a mess, and it's really hard to follow. And we were measuring this at 15,000 frames per second, and I thought, well, maybe if I can start to understand what's going on in the first 100 frames, then I could manage that or whatever. But it quickly became apparent that I wasn't going to be able to understand what was happening in the first 100 frames after a strike. It was going to require maybe the first 1,000 frames, or more likely the first 2,000 frames. And so we needed a different approach, right? And so here's the challenge, as you can kind of see. We want to make sense of the high-speed video data, but there's a lot of noise. The images, the individual frames that we get from the high-speed camera are inherently more noisy than those time-averaged frames that I showed you at the very beginning. And plus, we're generating a lot of frames, just generate a lot of data to look at. So it does turn out that it's relatively easy for us as humans with our eyes to recognize the patterns in there, but because of the noise in the frames, traditional machine vision wasn't going to be able to handle the analysis. So enter Zooniverse. This is a platform that is set up for hosting crowdsourced research projects, that's open for people to just take their data and post it on there and set up a project to invite volunteers. And the Zooniverse platform has thousands of volunteers, probably tens of thousands or hundreds of thousands of volunteers that are willing to participate in citizen science projects and do things that scientists ask them to do. It's been successfully used in various fields, notably in astronomy, but several projects have come out of acoustics as well. And here's the idea. We're going to crowdsource the data classification. All right, we're going to ask people to help us make classifications. So I want to actually do a quick demo of this. And if you go to this website, bit.ly/Steelpan vibrations, you should end up here. And, you know, once you click on classify, you get presented with this screen. And the idea is that you're just supposed to draw a circle or an ellipse around all the antinode regions that you see. And then once I draw an ellipse around this, then it's going to ask how many fringes are there. And so what I usually do is I usually count the fringes before I draw the ellipse. So this one has 1, 2, 3, 4, 5, and then I'll count this one as 6. So I'm going to draw that ellipse, and there's the pop-up window, and then I mark this as 6. I say okay. This one down here is really just, I count the bright fringes, me personally. Everyone does it a little bit different, but we ask multiple people to look at these. So on average, we think we're getting the right thing. So I'm going to count this as 1. Up here, I see like maybe 2 fringes up here on this. I don't really know what this is, but that's okay. I can figure it out later in the analysis. And then this one, maybe there was only 1 in that one. And then this is where the actual strike happened. And this, all the fringes are mostly run together. And so I know because I've done this many, many times, 10 fringes is the maximum that you can distinguish individual fringes on. And so I'm going to mark this as 11, which really just means we don't actually know what the amplitude is, but it's more than 10 is what it tells us. And so then I'm done. I have this option if I want to talk about how cool this picture look. I can click done and talk, or I can just click done, and it'll submit it to us, and then another one pops up for me to try to classify that one. So that's how our volunteers do all the work of making our classifications for us, which is really great. But then we have to analyze that. All right, and so on our end, we ask several people to analyze each frame. And so we wait until several people have done that, and then we extract their classifications, and we try to only take the ones that people agree on, and then average them all together. So this is a frame, and each of these blue shaded in regions are average ellipses that have passed the quality checks. And so we have this algorithm that figures out where there's a cluster and figures out where there are the outliers. Now you see here there are 3 clusters, but it says here that there's actually 4, and the 4th one is down here. This means that several people actually thought that there was nothing in this one, which is not great, but it's okay. Or they maybe tried to mark this. That's something that we always go back and look and check on. And then we only keep the ones that more than 5 people agree on, and we make the average of those. So our big challenge, though, is still with the numbers. We settled on a corpus of 13,375 images. We ask for 15 classifications per image, and that works out to 200,000 classifications, over 200, for only 7 drum strikes, which is a lot, right? But we have really good volunteers, and they put a lot in over the past few years. This is right after we launched. This is the summer after we launched. We had a concerted effort to get people to do some more classifications for us. And we had the summer after that, we had some more people, or no, this is the Citizen Science Month is when this was, and then the beginning of that next summer. And then this year, right when the pandemic was in, you know, people were locked in, and then it was also Citizen Science Month. We got a bump due to that. But we're always looking for more classifications. But without waiting for all of our classifications to be done, we wanted to make some analysis of this. And so we settled on looking at the motion of the octave note, because we really think that part of the distinctive sound is a delay in the time that it takes for the amplitude to reach a maximum for that octave note. So it's like the main note gets struck, and then there's a delay in the energy that's transferred to that other note, and we want to see if we can measure that. So you can see that there seems to be a trend here. There's some noisy, some noise out here, which is maybe some extraneous measurements or not good averages. And then there's these distinctive lines, which are, these come from not enough people actually measuring or making classifications, so we can't get good averages. And to me, it just looked super noisy, you know? So I was a little, you know, stuck figuring out where to go from here. So it turned out that at an acoustical society meeting, there was another musical acoustics person that said, hey, I think that the machine learning techniques that are out there would actually be really, really good for analyzing your data. And I said, well, okay, well, let's try it. And the idea is that I'm not going to talk about how the machine learning works specifically, but the idea is that we take our volunteer classifications, and then we use those classifications to seed a machine learning algorithm, which will then make predictions on what the actual, what people would possibly come up with for a measurement of the locations of the antinodes and for their amplitudes. And so here's what the machine learning algorithm spit out as a video. So you'll see the green ellipses that are identified by the machine learning algorithm. There they are. And then the numbers that are running over there are also the amplitudes that it's predicting. And so you notice that there was this delay after the strike before this started vibrating. And it's that delay that we really want to try to characterize for all the different note strikes. And then if we can get other information out, that would be great too. So how does this machine learning algorithm compare to just looking at our volunteer data? Well, here's the volunteer data again. Notice that I have the amplitude in terms of number of fringes on the vertical axis. And then this is time, which I put in terms of frame number, which maybe not great. But then when I plot the output of the machine learning algorithm, what it predicts, I plot again the amplitude in terms of number of fringes, and then I converted it to time in terms of seconds. So that's probably better. And you know, it still looked a little noisy to me. And I liked that I could see this amplitude increase in the first part of the right after the strike. But I decided that what I really needed to do was look at a smaller range of data. So I decided to look at just this range and see, well, what can I tell from that? And the question is, does this data actually represent the motion of the note? Because if it doesn't actually represent what the note is doing, then I don't know if I can trust the machine learning algorithm at all. So it turns out that the electronic speckle pattern interferometry output should follow a cosine squared, or I should say absolute value of cosine function. And so I plotted it to that, and it turned out to fit incredibly well. And in fact, the frequency that it predicts is the D5, which was the note that we were looking at. At least it was close enough to the D5 that we were very comfortable that this is actually working. So what can we say about the Steelpan now that we've done all these things? Well, I think we've learned that the volunteer classifications can be used to see the machine learning algorithm. It's not perfect yet, but we're still working on it, but it shows great promise. The machine learning algorithm can accurately extract frequencies of notes. I've done this on a couple notes, and it seems to work. We can get that measurement of the time for the energy transfer between notes. It looks like it's on the order of 30 to 40 milliseconds that it takes for that vibration energy to go into that octave note, which is really interesting for a lot of reasons, but primarily we expect the speed of waves in steel is significantly faster than the speed of sound in air, and we would expect that the energy to transfer very, very quickly, but it seems like there's this delay. We still don't fully understand that, and we're still working on that. we can't yet distinguish the contributions from the resonances that are on the strike note itself, right? Because that particular note that was hit is going to vibrate not only in its fundamental frequency, but in its second and third resonances as well. And we haven't been able to distinguish that yet, but we're hopeful that we'll make some progress on that. And then just briefly say, what does this say about science? Well, it says, I think, that science is a process. That's something that we know, but it shows here that science is a process. I started with a question, and I had to be open to all these new directions in order to make sense of the data that I was starting with. And along the way, I shared my process with others and got help from others, and they helped me, and I hope I helped them, and it was really, really great. So that's where I want to end today, and I want to thank a bunch of people. I feel like I'm going to forget someone, but I definitely want to thank Tom Moore from Rollins College, who we made the measurements with his high-speed interferometry system. Scott Howley has been working on the machine learning algorithm, has been great to work with. The entire Zooniverse staff, I'm fortunate that part of the Zooniverse project is actually located at Adler Planetarium near me in Chicago, and so I can sometimes actually go and visit them at the Adler. And of course, our project has over 2,000 volunteers that have contributed to classifying the data. The entire JJC community, including all the support I get from the great staff, from IT to our department to everyone that has helped with this. Couldn't have done this without some students. Joseph Garcia and Matthew Lange were just two students who in 2 different summers worked on the code for this and really helped make progress with that. We got some support from the National Science Foundation. I really want to thank the Acoustical Society for being a great venue for me to share this with, and I thank Kita for this invitation today, and I want to thank all of you for tuning in today. So thanks.
Thank you. Thank you so much for that wonderful talk. I learned a lot, and I'm going to go ahead and open it up to our audience. If you have any questions or comments that you'd like to share with Andrew, go ahead and please put those in the chat. While people are maybe thinking of their questions, something that I would like to ask you, and maybe would be helpful for folks, is how did you come to start studying the Steelpan? You said that it's really important in terms of acoustics and prominent in that way, but how did you come to it?
So I came to it actually when I was a grad student. I went to Northern Illinois University, and the music department there has a big a big component is their world music program. And part of their world music program is a Steelpan program. And so they had, a tuner that was there, and now on the faculty at NIU is Liam Teague, who is just a phenomenal panist that's, known worldwide. And so there was pre-existing, my advisor, Tom Rossing, had a Steelpan program or research program that he was doing. And so I picked it up. And I was actually very fortunate to, at the time that I was a student, there was a visiting researcher from Trinidad and Tobago, Brian Copeland, who came, and I worked alongside him on a research project that was this. And so this project grew out of that, basically.
Great, thank you. Okay, we've got some questions here in chat. I'm gonna read some of them off. This one says, was the delay dependent on the fundamental frequency of the resonant frequency at that location?
Yeah, that's a great question. We don't know yet. So here's the delay for the for this octave, and we're still trying to iron that out. It's complicated because each pan is unique, right? And so because it's hand tuned, we're trying to be careful not to make too broad of a generalization on that, but yet try to get to that understanding. So yeah, not really sure yet.
So actually, another question is, there are other lead pan layouts that do not have adjacent octave notes, such as the radar pan layout. Have you considered studying a layout like this, as it doesn't fall in line with the idea that the sympathetic vibration from the octave note is what defines the sound?
I would love to do that. I would love to do alternative layouts and look at those and how they contribute or not. Because I mean, it's interesting because I really focus on this fourths and fifths, and it's nice because the most coupling, or the most coupled notes are already they're already in that neighborhood of each other. So it made it super easy to make the image of. But that doesn't mean that other notes aren't also contributing. And so on a pan with a different layout, it would be really interesting to see how that works. I would love to do that. Send me a pan, we'll do it.
Okay, here's one. Could this methodology be calibrated against a simpler instrument, like a xylophone? Would that assist the machine learning algorithm, or would the intrinsic complexity of the Steelpan acoustics rule that out?
So one of our hopes is that the techniques that we're developing with the machine learning algorithm are generalizable to other musical instruments or other vibrating systems. And to answer that specific question, I don't know if it would make it easier to go from like first the xylophone, then to the Steelpan, or which way, but in any case, we would definitely want to apply the technique to other instruments or to other vibrating systems. So that's something that we definitely have in the back of our mind and want to do.
Here's a quick question here. Why is it that you use a drumstick to resonate and not a tuning fork?
Well, so for the high speed measurements, we want it to as closely resemble the what the panist is doing. But for the time average stuff, we actually, so if I go back to the earliest things that I showed, for those, we're causing the Steelpan to vibrate at a single frequency. We did it electromagnetically, but it's very, very similar to if you were driving it with a tuning fork, for example. So I hope that's kind of answering what the question was asking.
Here's another question. Did you study strikes on the higher octaves, so at the center of the pan, and what did you learn?
That's a good question. I don't think that so in our on Zooniverse, actually on Zooniverse right now, there are only 2 strikes that you can make classifications of. And originally we had 7, okay? And in our machine learning study, we focused on the 7, and they are all from the outer ring. But I think I have on the order of 30-ish videos. And so there might be some videos of strikes from the middle ring, but I can't recall offhand. That's really bad. But it's something that we like to look at. And I always had trouble actually hitting the innermost ring and getting it to sound good. I'm just not a good panist with my technique. But
yeah. Okay, so here's a comment. So thank you for shedding light on the otherworldly sound of the Steelpan handpan. I've always loved to play it and have been curious how it produces a sound. I'm just wondering again about the setup of the first simple setup using the laser, mirrors, and camera. Was that using a high-speed camera?
This one the one that is on the screen right now does not use the high-speed camera. So you just need a digital camera that it's easiest if it feeds directly into a computer. But I've done this. I did it with a USB webcam, basically. I don't suggest that, but something a little bit higher quality than a USB webcam. But yeah, to get this, you don't need the high-speed camera.
Are the harmonics on an individual strike note harmonic? Is the area behaving like a drum head or a plate?
It's behaving like a plate, but the tuners have forced those resonances to be harmonic, the first three. And it's interesting that part of part of the interaction that the mallet has with the pan is that the rubber tends to dampen the higher harmonics, and so those first three harmonics, which are the most important and the ones that the tuner spends the most time getting in harmonic, are the ones that dominate the sound, primarily or in a large part, I should say, because the rubber is emphasizing it and damping most of the other ones.
Thank you. I skipped one here by accident. It says, how do you mathematically approach the alignment of the various partials in the tuning process?
Well, I'm not a tuner, so I can't speak to how the tuners do that, but specifically, but you know what the frequency is of each note that you want, or each note that the tuner wants. So C4 is going to be 261 hertz, and then they know that the second harmonic that's in that is going to be twice that frequency, and then the third one is going to be 3 times 260. So I often will skip to E because that's an easier number to work with. It's 330 hertz. So the tuner is going to, when they're tuning the second one, they will try to get it to be 660 hertz. And you can actually, because what the shape, and actually the tuners are smart. They know what these shapes look like. So they can, put their finger down right there where that line should be, and then hit the note and try to get that second, and then be able to tune that. So there's lots of techniques that the tuners use. And I just really want to emphasize, I'm not a tuner. I have incredible respect for the craftsmanship that they have.
Well, I'm going to ask a quick follow-up because you mentioned kind of in passing. So do you play the Steelpan yourself?
No, I do not. I occasionally, every so often, I try to teach myself a scale on the Steelpan. Yeah, but I'm not a player. I wish.
Thanks. Here's a question. What types of materials can be subjected to this interferometry test? I wonder if this method would work to test Helmholtz resonators or resonators in general to find if they match the theory.
So the technique works best if, let me see if I can, if you have something that is a flat surface that you can have the laser light shine onto and then reflect off of. And but I mean, flat is relative, but things like guitars, the soundboard of a guitar, violins, stringed instruments like that. But the technique has been used for curved objects too, like the vibration of bells, also very, very popular. Even brass instrument bells, like trumpet bells and trombone bells and things like that. So things that actually vibrate are really good for this. Things like a Helmholtz resonator, where you're looking at the resonance of the air inside the Helmholtz resonator, are more difficult to do. Now, some people have tried adapting this technique to measure air vibrations, which it can be done. It's very, very hard to do, very, very hard.
I wanted to share this comment with you. It says, I volunteered on Zooniverse on this project, and it is fascinating to see what you're learning from our efforts. Thank you very much for extending the invitation to join you in the presentation.
Oh, that's great. I'm so happy that the Zooniverse volunteers, some of them logged in. That's great. I'm happy to hear that. Thank you. Thank you for the classifications.
All right. We have a couple more questions here. What type of pre-processing techniques did you use on frames before feeding them to the machine learning algorithm?
Okay, not as much as you might think. Before feeding them to the machine learning algorithm. Okay, so okay, yeah. So I showed. That's actually a really good question. When I was showing this, all we did is we took out these measurements here, or these classifications. So those are outside of a cluster. And then everything that's inside of a cluster, we took all of the information and we average it all together. And we don't try to weight it at all. We just like, the information that we get is we get the size of the ellipse that every volunteer puts in. We get the number of fringes that they identify. And we also get a rotation of the ellipse, so we know how they've oriented it. And so then that's all averaged together. In the machine learning algorithm, which which Scott works on, one of the trickier parts is that rotation of the ellipse, because like we don't care if it's oriented this way or if it's like 180 degrees oriented the other way, but in terms of the algorithm thinks it should care or whatever. And so we have to do a little bit of consideration on that. But in terms of pre-processing, it's mostly throwing out outliers, averaging, and making sure that we start with a minimum of 5 classifications.
Thanks. Here's another question. Do you think using data from more sensors, maybe a microphone, might help the machine learning algorithm?
Oh, that's a good question. We have data from microphones. We have not tried to incorporate that with the machine learning algorithm. And I didn't feel like I was going to have time to really talk about it. But one of the things that we want to do with that microphone data is try to line it up with this and see how does the microphone data compare to this. So yeah, that's something that's a part of the overall analysis, even if it's not going into the machine learning.
Okay, and here's one last question and maybe proposal even. Would you be interested to build a virtual prototype of a Steelpan, maybe to explore and discover new sounds?
Well, I think that, I mean, yes, I guess, yes, I would be interested in something like that. But one of the things we've thought about is whether or not we can have a computational model or a finite element model, maybe, where the computer would be able to answer some of the questions that we can't resolve. And so I do think that there is a place for doing that type of work side by side with this. I think they can inform each other is basically what we hope.
Well, again, I would like to thank you for taking time to speak with us today and answer some questions. I suspect that we have some folks in the chat who are really interested in learning more. Are there any places you'd like to direct them to go? Perhaps the Zooniverse?
Yeah, definitely. Please go to that link. I hope it worked. And help us out there. And on that Zooniverse page, there are a few ways that you can find to contact me. I think people like my Twitter handle is linked there, and you can find me, send me an email or whatever. I'm always happy to talk more about this sort of thing.
Great. All right. Well, I'm going to go ahead and wrap it up here. Thank you again, and thank you everyone for joining us. Don't forget to register and attend our next talk in 2 weeks with Dr. Nicole Holliday. All right. Thank you, everyone.
Thanks, Keita.
Bye.